Hello everyone. Um, yeah, sorry, I am 2 minutes late. I was having problems with my internet, so I had to restart my my modem, right? So give me a second. Let me share my screen. Okay. Yeah, new desktop image. Yeah. Do you like it? It's North Vancouver. Yes, I did. I took this picture on Saturday. Thanks. Okay, and give me a second. Please give me just one more minute because, of course, I was having problems with my internet, so I need to upload the PDF from today, right? So can you check our webpage, please, and check if it's, yeah, it's there. So PDF, and yes, okay, good. So, okay, so learning goals for today, we will talk about textures and something called map channels. A map channel is basically just an algorithm that takes a texture and does something, right? It's the way you use a texture is usually called map channel. Okay, so this is what we were discussing last time, right? In order to create a beautiful image or to represent an object with a specific material, we need, at least in real-time rendering, right? So right now I'm still talking about real-time rendering. We have these different components, right? So these are called components. Ray tracing will be a whole assignment. Yes, oh yeah, Jake is basically telling you about the ray tracing. Okay, so we have three different components, right? The component of ambient, then the diffuse component, and the specular component, right? And remember, ambient is just how does this object looks, right? With light coming from everywhere, right? And this is just to avoid having an object that is basically like pitch black on the other side of the light, right? Then you have the diffuse component. This is usually what we relate with as the actual color of the material, right? You will see that when these are basically different channels. So usually in Maya, Blender, 3ds Max, and any other software like that, the color of the ambient channel and the color of the diffuse channel are usually the same, because in the end, these two channels, they carry the color of the material, right? And usually you define it on the diffuse channel, right? Even in your code, for example, you can basically define it on your diffuse channel. Then you have the specular, right? It's basically how the light is basically behaving on your surface and how like shiny is your object. And again, that depends on the microstructure of your material or the surface, right? So we already talked about this. This is one option to compute this specular component. Remember, when we are talking about this model in particular, this like computing the normals, the dot product between the normal and this type of equations, either Phong or Bling or anisotropic. What we are talking about is from the specular component, right? And we already discussed this super basic Phong, and this is basically very similar to the code that basically you will use in your assignment. This is a very large chunk of your assignment already there. And we also checked the demo from Alec Jacobson. And again, just by reading and studying the demo, you can see almost exactly a very large chunk on your next assignment, right? And so we said, right, in the end, we have these three components, ambient, diffuse, and specular, and we have these numbers here, K ambient, K diffuse, K specular. Can somebody remember me? What are those things? What is, for example, K diffuse? Yes, exactly. Those are weights, right? So basically, playing with those numbers, I can just like increase or decrease how much is component contributing to the final color, right? So for example, if I decrease the color of the ambient color, it will look that like maybe the object is maybe in a darker area, right? Because now this fake lightning that is coming from everywhere is not as strong, right? So it will look like, okay, it's maybe in a darker place. Because of course, if you have an object in a completely empty room with only one source of light, maybe, I don't know, maybe your cell phone, for example, yeah, I mean, the one side of the object will appear like brighter, and the other side will be completely black or almost completely black, right? If we are like, imagine you are inside a stadium, right? There are no walls in which the light could bounce, right? So yeah, sometimes we need it. Sometimes we need to play with these weights to decrease or increase the contribution on any of these components, right? And we discussed about Blinn. Blinn is very similar to Phong. It's just a bit less expensive because we are just getting rid of one dot product, right? Okay, so now let's talk about, yes, the use of textures. And because it's October, and so I don't have the dragon anymore, I don't have the bunny anymore, so now we have a pumpkin, right? Yeah, because it's October. Okay, so let's talk about textures. How can we use textures to achieve different stuff, okay? So let's imagine that we take that model, right? And we just like use a specific color for the material. This is basically this could be the result of a very, very basic either Blinn or Phong. In this case, I'm using Blinn, right? Someone says look like a garlic. Yeah, by the way, this I made this 3D model. This is not actually a pumpkin. This is a, I don't know if you have been here in Vancouver. They sell this like decorative pumpkins that I think they're called squash, right? So they're not exactly pumpkins, they're like squash. So they're like smaller and they have like a very intricate texture. So I think it's, yeah, I mean, the one I took for creating this model in particular, it was a squash actually, not a pumpkin. So yeah, so basically, yeah, we created something, a very basic Blinn material, and this is what we have, right? So, but what happened if I want to make it look a bit more realistic, right? Well, I can create a texture, right? I can create a texture with details, right? With the color details. So that is basically one of the first, or maybe the most obvious use of textures, right? Taking a texture and just grab the color and use the color in your equations. And again, today's lecture will be more conceptual. I will show you what can you achieve with your with textures. And next lecture will go like in more like details about like the technical details on how can you actually implement this. But for now, it's just conceptual. So the thing is, as far as we have been working right now, the color that we are using on a fragment shader, right, comes from a varying variable, right? That is basically the color of the material color, or whatever you want to name for that variable. And from where does that color comes from? Usually from the vertex shader, right? So the vertex shader has a varying variable called whatever, pumpkin color, right? And we can actually determine the color, for example, in our JavaScript, right? So this is what we were doing until now. The thing is, it is possible, obviously, in either OpenGL or WebGL or 3.js to get a texture. And you already have a file that actually that has a texture. The transformation assignment, right, has the floor, and the floor has a checker material, right? So you can see the code that you need, right, to like literally like grab a texture and show a texture on an object. It's already there. It's already on your template, right? So what is happening there is that the vertex color is not defined on the JavaScript. The vertex color is being reading is read from a file, right? So this is what you do, and this is the after, right? So before, after, we are basically getting a way more realistic object just by getting a different texture, right? So that is basically the most obvious application of color, of textures, right, as material color. There are other types of effects, right? So for example, this is another type of effect when you want to use a texture to define surface details. And there are in general two types of images and two types of channels that you can use to define different detail. So one of those is called the bump channel, and the other one is called the displacement channel. As you can see, the type of images are different, right? So the type of image used for bump channels are usually grayscale. So basically you have an image that it's in black and white, right? And bump channel will do is it will basically distort, right, the way you are computing the normals. So basically it will basically distort the normals, right, to mimic the effect of your surface to have a certain pattern or a certain surface detail, right? Displacement does exactly the same thing in terms of like adding more texture, but this is similar to what we were discussing between interpolating normals and actually tessellating the geometry, right? So I will explain you with an example. So let's pretend that we have this texture right here. This is a texture called I think the name of this in particular is cell noise. Well, whatever. I don't remember. There's this algorithm. It has a very specific name. I don't remember. Yeah, it is based on Voronoi. Thanks, William. Yeah, it is based on Voronoi, but it has another name that I just can't remember right now. But by the way, this is a type of texture that is not coming from, for example, a picture. This is coming from a procedural algorithm, right? So first thing that we need to also understand today is that there are different types of textures. There are textures that we can, for example, go and, I mean, you can take your cell phone and you can like take photos of grass or maybe a tree or whatever, and you can use that photo, right, from your cell phone and maybe make a couple of processes on Photoshop or GIMP, right, and you can use that directly on your computer, on your renders. But that is a bitmap, right? That is that type of images. They're called bitmaps. But there's another type of textures called procedural textures, right? So can you remember me what does procedural means? What do you think it's a procedural texture? Okay, that is automated, not exactly, not made by an artist. Yes, exactly, it's created by an algorithm. Okay, so this image in particular, this is not a photography or something like that. This basically is created by an algorithm, and I will show you later. So let's imagine that you take that, right, and you use it on your diffuse channel, right? So when you use a texture and you are grabbing the color of the texture and directly using as material color, what you're doing is you are taking a texture and using a diffuse channel. So we call, in computer graphics, we call channel to the use of a texture, right? So this texture applied to a diffuse channel, it will look, your pumpkin will look like this, right? However, if you take the same texture and instead of using the texture as diffuse channel, you use it as bump channel, this is what it will look, right? So it's exactly the same image. It's just the way you are reading those values and the way you are using those values is just different. And again, remember, all of this can happen in your code, in your fragment shader, right? So basically, you get all the information. You get, for example, the texture from your JavaScript. You send that information, right, to your vertex shader. Then from the vertex shader, you send everything to your fragment shader. So once you are on your fragment shader, you have a variable that is basically the color of your texture. How do you use that variable? It's up to you. So if you take the variable from your texture and you use it as the color in the diffuse component, it will look like this, right? If you use that variable to modify and you basically generate an equation that basically is modifying the normals of your surface to like fake a different normal, right? Now it's called bump channel, right? Or what you are doing is what a bump channel does, right? And someone is asking, does the bump channel change the shape? No, in this case, it's not changing the shape. It's a bump. The bump channel or the bump effect is it's a fake. So as you can see, the border of our object is not changing, right? So look at this. This is before, after, right? So look at the border. The border is not changing, right? So there is no change. So the geometry is not changing. The only thing that it changes is the normal that you're getting, right? So basically what happens is, usually when bump channel, what happens is that color white, it will be it will be read, right, as a higher surface, and the color black, it will be read as a lower surface, and obviously any gray color will be basically in the middle of that. So you modify your normal depending on how black or white is your texture in that specific fragment, right? How we do that, yeah, we will see that later. Some of those things we will see those examples on our lectures. Some of those you will need to investigate by yourself and like read a couple of books, because again, that is part of the research that you will need to do for your assignment, right? But it's very simple. The majority of all the things that I will show you today, except for one thing, they're very simple, and they're like 1 or 2 lines of code. Yeah, literally 1 or 2 lines of code. Okay, so again, bump mapping is just taking that color, modifying the normal based on that color, and fake a different surface. Okay, there's another type of effect called displacement, and this one is different, right? I mean, as you can see, this one is way different, right? This is by the way the type of like texture this type of like decorative squashes have, right? And someone is saying it has cancer. Wow. Okay, that is horrible, but yeah, maybe. So what do you notice in terms of geometry here? Do you think we have new geometry or not? Yeah, the edges are changing. New geometry, right? And it got bigger, yes, that is true. So basically remember that one of the examples that I've shown you for vertex shader is that actually it was on our midterm, by the way. It is this very simple code in which we are taking the current position of the vertex, then we take the normal, right? And basically we were scaling the normal with a factor and then adding to the actual position. So basically what we were doing is like inflating the object, right? Remember that example? I've showed that piece of code many times, and that was actually the piece of code that you needed to debug on your midterm, right? So it's like inflating. This is exactly what is happening here, right? The thing is you need more geometry. So in this case, this is exactly one of the cases in which you will need to activate tessellation, right? Because with the original, right, with the original geometry, there are not enough triangles to move, right, and to create this like bumpy effects, right? So you obviously need to tessellate, right? You agree? How much do you tessellate? It will depend, and some of those things are sometimes automatic, right? I mean, there are just a couple of lines of code that you can like just call your GPU and say, okay, just tessellate this, right? But displacement is a bit more complicated, right? Again, so but what is happening here again is that instead of just faking the normal, right? What you would do is you need to first tessellate. So you increase the number of triangles. You obviously increase the number of vertices, and then for those vertices, right, at vertex shader level, when it's already tessellated, right, you move them along its normal. But because the normals are also modified, because you are also using these colors to modify the normals, this is basically what you have, right? So that's why the object is not only changing on the borders, it's actually also like inflating, right? It's getting bigger because the vertices are actually moving along its normals, but not the original normals, but these like fake normals, right? Nam is asking, change the height fill. Yes, I mean we don't call it, or maybe some do, but I've never heard someone call it height fill. That is the term height fill, by the way, is more used on terrain. So, for example, imagine if you open Google Earth, as you remember, for example, you can see Google Earth, and you can apply like the 3D view in Google Earth, right? And you can see not like a flat picture of I don't know, Vancouver, but if you apply the 3D, you can see literally the elevation of the mountains of Vancouver. And so you can see like Grouse Mountain and all those mountains like very realistically, right? So the elevation information that is used at Google, for example, to create those types of things, it's called height fill, right? So yeah, but I think that is a term that is more used in geomatics. Geomatics is the use of computer science and computer graphics for creating imaging related with geography. I did in 2011, yeah, well, 9 years ago, I did a research internship at Laval University in Quebec, and I was working actually on the geometric department, and yeah, we basically use height fields. But yeah, but in some sense, Nam, you're correct, because what we are doing here is we're basically like elevating the surface of this pumpkin, right? Depending on a black and white or like grayscale map. And if you go after the lecture, if you go to Google and you search for like height fill terrain map or something like that, you will see that is exactly what you also do when you are modeling terrain. Okay, good. So as we said, if we want to like create displacement, you obviously need to tessellate, right? Okay, so first quick stop. Do you have any questions? Yes, Nam has a question. Yeah.
So why is tessellation necessary? Can't you just do a low resolution displacement?
Very good question. Yes, you can. Okay, let me just go back. It's not that you literally require, that is true, but imagine that with the original geometry, I just apply the displacement. The thing is, you will not see this amount of detail, right? So yeah, I mean, it will work, right? Your vertices will move, but not just, yeah, without this amount of detail, right? So in order to see like this detail that you are seeing here, right? I mean, here the geometry is like literally copying all this like intricate texture here. In order to see that, you need to have, yeah, millions of triangles, right? But by the way, again, this tessellation is done automatically. I was using, I think for this image in particular, I was using Mental Ray, which is a render engine. It's actually a bit old already. It's very old, actually. It has more than 10 years.
So you're saying somewhere in the pipeline, the GPU actually looks at the displacement channel and decides whether to tessellate or not?
Yes, you can also do that. Yes, for sure. Yeah, you can ask that to be automated. Yeah. I think maybe I'm wrong, but as far as I remember, DirectX is better in that particular task than OpenGL. Maybe I'm wrong. Maybe the new versions of OpenGL are better or are getting better. But in particular, doing this like very quality displacement thing, it's usually better in DirectX. DirectX has very specific libraries, and they have a couple of patents regarding that. Because I don't know if you remember, and this was I think I mentioned this on the first lecture. I think DirectX has something very cool, that is that they have an optimized dynamic tessellation. So the tessellation in DirectX happens not for for the entire surface of the objects, but it depends on how close the objects are to the camera. So it is a way more sophisticated way of creating this tessellation. So it is totally automatic. I mean, you as programmer, you basically never touch that. If you just like I mean, you obviously need to activate a couple of things, right? But you don't need to write the tessellation algorithm, because they have a super sophisticated algorithm that depends on on how close the surface is from the camera, and how much detail your displacement map has, right? Depends on that, it performs the iteration, right? So it decides how many triangles need to subdivide and how they need to subdivide. And actually, displacement can be super sophisticated. Sometimes they even use Bezier surfaces. They literally create Bezier surfaces on the fly directly on the GPU, depending on how is your map. But it's like super sophisticated technology. Yeah. Okay. So another question.
Hi.
Hello.
I just want to know why there are more like bumpy thingies on the display channel comparing to the bump channel. Is it because, like as you said before, like the vectors are moving along the fake normals?
Yes. Yeah. So look at the texture here, right? The texture actually doesn't change, right? So for example, we have a cell here, we have another cell here. So the number of cells is not changing. I use exactly the same map. I just I use exactly the same texture. I'm just using it in a different channel, right? So what is happening here is the bump channel, it doesn't need to create new geometry, right? It just fakes the normal, right? So this yeah, this surface right here is not real, right? I mean, the details on this surface here is not real. It's just the normal that is faked, right? So obviously the lighting is changing, right? It's just the way you are defining the light, right? However, here it first tessellates the object. It creates millions of polygons. Actually, in this particular image, I think this has probably more than 10 million triangles. The amount of detail I put on this image in particular is huge. I mean, maybe maybe you can see these tiny artifacts. Can you see like tiny
Yeah.
artifacts? Those are triangles. So the amount of triangles here is like impressively high. And so now basically, because it's on displacement channel, now it's taking these fake normals, but it's moving the vertices of those new triangles along those normals and creating this bumpy effect, right? But yeah, this is obviously way more realistic, right? Because you literally have more information, right? More triangles.
Right. So there's actually another question.
Yes.
What is the fake normal that you what do you mean by the fake
Okay.
normal?
So remember when we are computing the lighting, right, in a Phong, let's say Phong or Blin, right? What information
Mhm.
do you have? You have the information. You have the position of the light, for example. You have the vector from. You have your view vector, right? And because we are dealing with a fragment, right, and a fragment is a portion of a triangle, you also have an interpolated normal that comes from the vertices of that triangle. You agree?
Yeah.
So at the fragment level, right? If you don't do anything, you already have that. You have a normal that is an interpolated normal. So when I say fake normal, what I mean is at that level, in that code, in the fragment shader, you read the texture, right? Actually, you read the texture on your vertex shader, and then you pass the color. So basically, imagine that you on your vertex shader, for each vertex, you have the interpolated normal, right? And you
Mm.
have, for example, the color of your material, in this case orange, and you have the color of your texture. And let's say that for that particular fragment, the color of the texture is, I don't know, like some degree of gray. Okay, so you have a code there, or you create a code there that depending on the amount of white or black or gray of that color, of the color of your texture, you take the normal that you right? The normal that you got as interpolated value from the vertex shader, you take that normal and you modify that normal. You modify that normal. So basically, that's why it's called a fake normal, because the actual normal of the surface is the one that it had or like before, right? With the original triangles, right? But if you're you're using a bump mapping, right? Depending on the color of the texture, you basically imagine that you're going to like rotate the normal, right?
Mhm.
So that normal is not exactly orthogonal to the surface, right? It's a fake normal. You will use that normal to compute your color, right? But it's not the real normal. It's already distorted. It's already modified, right? Is that clear?
Yeah.
Yeah.
Oh, yeah. Thank
Good.
you.
Okay. Okay. Another question. Can you have another question?
Yes. I do have one question for the tessellation. Maybe the next slides after the displacement.
This one?
Yeah. This 3D image with after the tessellation image. Do we do the tessellation for the quads over here? I'm a bit confused with.
Yeah. In this example in particular, the original model is not made by triangles but made by quads. So yeah, the tessellation in this model in particular, the tessellation happens at quad level, not at triangle level.
Oh, okay.
And there's another thing. As I said before, if you see this image, the amount of triangles that the tessellation here is doing is huge. I mean, again, I have literally millions of triangles. So what I am showing here is just an example of how a tessellation look, because this is not the actual tessellation that was performed to create the past image. If I show you the exact like the right amount of triangles, because I'm showing like the border of the edges, right? The entire image will look completely black, because those triangles there are so many triangles, millions of triangles, and they're so tiny that basically the image will be completely black and you will not even understand the amount of geometry that is there, right? So yeah, so this is just like an example, right, of how this model look when you tessellate the model, right? But it's not the actual tessellation that it was done for the previous, right?
Okay, I understand.
Good.
Yeah, thanks.
Okay, good. And again, I prefer to like hear your questions, but let me maybe check a couple of questions from the chat. So Gloria was asking, what is the difference between interpolated vertex color and ambient lighting? Okay, the vertex color, right? The interpolated vertex color is the actual color from your material, right? Usually that is the color of your material. And the ambient lighting is, I mean, if you're talking about color, the ambient lighting color is the color of this fake light that is coming from everywhere, right? So remember the ambient component is like faking how the object will look if there were light coming from everywhere. And again, I use the word I use the word fake a lot because almost everything is fake, right? I mean, when I say fake lighting, is because we are not literally creating lights, right? We have no photon emitters coming from everywhere. Yeah, it's just an effect that it looks like a light coming from everywhere, right? Okay, so let's continue. Okay, so basically, again, if you have, for example, color and now displacement, and I will explain a little bit why these textures are kind of like a bluish, right? Basically, if you combine those, you can get from here is just texture, right? It's basically just color. So you can get subtle realism to your material. So for example, in this case, I'm not getting this like bumpy effect, but please look at the surface and look how the surface looks different just by having these fake normals, right? So at this level of fragment detail, you can get pretty nice results, and the steam also is also interesting, right? So in this case, for example, I am using displacement here, and so as you can see, for example, the map for this part of the pumpkin or the squash, right? The places in which it has details is basically on these like tiny spikes. So here the software, it needs to like tessellate the surface in those regions, right? And then just again elevate the position of those vertices, the tiny triangles that are tessellated here, and just and create this effect, right? So we are actually creating new geometry here, and it looks good, right? Tommy's saying almost everything is fake. Yes. Yeah, computer graphics, we need to fake a lot of things, right? I mean, mimicking the reality is just not achievable sometimes. Okay, so the thing is, math is fake. No, math is not fake. Okay, so so the thing is, I was showing you basically two types of maps that are used to show surface detail, right? And one of those is basically like this, like this bluish type of material. So let me show you something. Let me show you this image. Give me a second. Okay, so let's see this image from. Let's take a closer look to this image. Can you see? Like in this zoom version, right? Okay, so this type of images or this type of textures, these textures that they look like purple, pink, blue, things like that. These are called normal maps. Okay. So whenever you're, if someone is like creating materials and creating this surface details to something, and they are using a texture material, either a bitmap texture material or either a procedural, sorry, no material, texture, an image, right? Either a bitmap image or a procedural image. If it's like grayscale, those are bump images, right? If it's this like bluish image, they're called normal maps or normal textures. The difference is how the information is encoded. So as I said before, when we are using the other type of textures, the ones that are like grayscale, white means higher surface, black means lower surface. So basically the only information you have in a bump material is just like elevation information, right? If the surface needs to like move up or down. Here we have more information. What you're seeing here is the color of any of these pixels, right, is RGB, right? So the way you take this type, the way you use this type of images when these are normal textures is that the RGB color from this image here, you take it as X, Y, Z, and you literally take those values and use it as normal, right? So actually, it is way more interesting because this image is showing direction of surface, right? And that's the reason is they're always like in these grades of like shade of like bluish and purple and things like that, is because they're basically showing you a vector that is like moving in a half of a dome, imagine like that, right? And those vectors are unitary. So basically, if you take the RGB value from any of these pixels, you will see that those RGB values, right, they are basically representing a normalized vector, right, a unitary vector. And again, you just take that color directly as your normal. So for example, in the case of bump maps, I told you that you need to create your own equation, or you need to create your own like algorithm to take a value that can be white, gray, or or black, right? And depending on that color, you basically need to like modify your normal, right? But it's not trivial, right? You need to see how do you modify your normal, because you only get elevation information. Here is different. If you assign you send this texture to your 3.js shaders, right? Or yeah, to your fragment shader, and you get this as a color. You get this as a varying variable as color, right? And basically you get this on your fragment shader as a color. On your fragment shader, you don't need to do anything, but literally like rewrite your normal with the information that you're getting for that color in particular from here, right? And yeah, and let me show you the other map, the one from the pumpkin. And again, if you want to like find this type of maps, if you go to Google and you type in Google like normal texture map, things like that, you will see a lot of images, and you will see this type of information, right? So for example, here we see the other map, the one from the Steam, right? So basically this color here, right, is the RGB values from this guy is a normal that is like pointing outside of our monitor, right? And the other colors, right, they're just like normals or like vectors that are pointing in that direction or in this direction or in this direction, right, in different directions. So this information is getting, the shader is getting exactly the color of this image, literally only the color, and is modifying the vertices using that vector as a normal, right? Okay. Okay, let's continue. Okay, good. So that was one possible use of textures, right? Basically, give more detail or yeah, define the surface detail. You can also you can do almost anything else, right? The thing is, remember, you are defining at fragment shader, you are defining the final color of the fragment shader, and this is not only the RGB but also the alpha value from the fragment shader, right? So you can get any texture and take the color of that texture and use it as yeah, whatever you want. So this is another example. You can modify the alpha value from your fragments depending on the color you're getting from an image like this. So this will be the before and this will be the after, right? I can, for example, in this case, I am using the color, the white color, I am using it as 100% opacity. The black color, I am getting this on my fragment shader as 0% of opacity or 100% of transparency, right? So this is basically what you get, right? We already discussed something similar to this. We were saying that, for example, if you want to like create like grass or hair or things like that, this is basically what you do. You get a channel that has some information, either because your color texture has an alpha value and you're getting directly the alpha value, or you can also use a black and white image and take either the black or the white, right, in your fragment shader and decide, okay, if the color of this texture is exactly black, I don't care about the color anymore in your fragment shader. I don't care about the color anymore. And you just put your alpha value to 0 and that's it. It just gets transparent, right? And for example, by the way, here, because I'm basically like making like cutouts to my pumpkin, I am not activating the backface culling, right? If I activate the backface culling, sorry, I will not be able to see, for example, these fragments here, right? Because these fragments are literally pointing to the other side of the camera, right? But I'm seeing the back side of my surface. We can also play with the specular level, for example. Again, you're computing the lighting, you're computing the color, and you have a lot of variables there, right? So we have, for example, the glossiness, we have all these weights, right, for every component. So I can, for example, increase or decrease the amount of light that is reflected using a map. So in this case, for example, I am taking the color of this map, and depending if it's white or black, I am deciding if the object is shiny or not, right? So basically what I'm doing here is just multiplying or getting this value, either 0 or you don't you don't like it. Yeah, of course. Yeah, it doesn't look nice, right? But I am taking basically if the value is black or white, I can use this as black as a 0 or 1, and that I'm using that as my k specular, right? Which is basically the multiplier for my specular. And so this is what you can get, right? The thing is, yeah, maybe you don't like this, but you can actually create a very specific texture that will control how your object looks, right? In terms of the specular level. So for example, here, this image is way more intricate, right? And look what happened if I apply this to my specular level. Again, I am using either the black, white, or gray as the multiplier, right? So maybe it's not as obvious, right? But this surface here, it doesn't look as realistic because it looks like plastic, right? But here, this subtle change, right? It makes the specular level be not as perfect, and you have a certain like texture detail, and you're just adding realism, right? So that's basically just another way of using your textures, right? And in the end, imagine that you basically combine everything, right? So you can use like diffuse and displacement and specular and bump and everything. And you can do things like this. You can create like a very intricate, mutated pumpkin or squash with some healthy problem apparently, because yeah, I mean, yeah. The thing is, I mean, the actual decorative pumpkins like this, they usually have this type of like texture. Okay. Yeah. So basically, that's how they look. Okay. Okay. Questions? Because yeah, we finished for today. Yeah, Nam has a question. Yeah, Nam.
I'm still not sure why specular channel is entirely necessary, because why not just simulate lighting after applying the textures?
We are okay. Maybe I don't understand your question. I'm not
okay,
saying.
so does
give me a second.
does specular map? Oh yeah.
It's not necessary. It's not exact. It's not required. These are just optional things that, right? What I'm showing you here is that you shouldn't be restricted to, oh, a texture is only for defining color, right? Basically what is happening is you will get textures, right, on your fragment shader, and you can use those textures to do whatever you want, right? So any number that is on your lighting equation, on your material color equation, right? You can modify those variables using textures, right? So yeah, maybe in this case in particular it was not as obvious. Let me show you another image, and maybe it will be more obvious, right? And why sometimes you could use it. So for example, let's see this image here. You can also, for example, use maps as mask, right? So for example here, yeah, maybe the quality of this image is not too much, but when I did this model, for example, can you see the details on the window?
Yeah.
So for example, this window is transparent, right? Some parts of this window are transparent, and the other parts of this window are like made of gold, right? So here, for example, I'm using a map, I'm using a texture to mask in which parts of the model I want the material to behave like a crystal, like glass, right? And in which other parts of the model, or in which fragments I want this guy to behave as gold, right? And the amount of specular level, it is different, right? Because gold, right, it should have a different behavior in terms of specular level than wood or any other thing, right? So for example here, right, you can see maybe here you can also see that the gold detail that you can see here, right? The gold is shining more than this painting here, right? So this is basically performed, or this is done by modifying the specular level, right? Using, I'm trying to see if I have another picture, another close-up. Yeah, no, these are. But yeah, is this clear? Is that clear?
Yeah, it's pretty clear. Just a follow-up question is, so that is if you choose to include the golden strip as part of the window, but if you wanted to actually make the golden strip its own geometry, the specular map wouldn't have been necessary.
Yes.
Okay,
Yes.
good.
Yeah. Okay. Great. So thank you so much, everybody. I will see you on Wednesday. Bye.